Hello. So we have already covered the following subsections. We have talked about equilibrium and LTE hypothesis, properties and states, and specifically system states. So our task now would be to discuss how do you classify properties and what is known as flow states. So let's start with a concrete example first. So suppose we have a block of copper and a system state, state 1, and another system state, state 2, describes it. So in other words, the moment you hear about state 1, state 2, you can immediately think, what is state 1? It's a collection of pressure, temperature, etc., velocity. We know we have covered all kinds of properties, P2, T2, volume 2, volume, velocity, kinetic energy, potential energy, etc. So how can we keep track of this expanding list of properties? We started that process in our last lecture, last module. We'll just formalize that even further now. So let's look at properties in terms of what is it, what are the group of properties that describe different features of the system, of the state. First of all, we've already seen that all properties can be either extensive or intensive. Once again, what is the difference between the two kinds? Extensive properties are additive. If you have two identical systems and merge them together, the properties will double. Example could be mass, volume, energy, of course, all the components of energy, entropy, etc. On the other hand, intensive properties could be, we already are familiar with pressure, temperature, molar mass. So if you have two identical systems, two copper blocks at the same temperature, and you put them together, the temperature is still the same. It hasn't added, it doesn't add up. Same with pressure. We also saw that some of the extensive properties, when you divide by mass, we call them specific properties. Recall, what is specific properties? We divide by mass. Then we get some of the, look at that, mass divided by mass is 1, so it doesn't matter. Volume divided by mass becomes specific volume, specific stored energy, specific internal energy, specific entropy, which is small s. And notice that our symbols for extensive properties are capital letters, and when we divide by m, they become lowercase letter. Mass, of course, is an exception because in mechanics we always use small m for mass. Similarly, specific properties as well as intensive properties, we try to use lowercase letter, but exceptions are temperature and molar mass. You'll also see that the specific properties are also intensive. Why? Because they are independent of mass now. So we can put an arrow here saying that all these properties are also intensive. So these are intensive, same are V, E, U, S in this particular example. They're also intensive now, except these are inherently intensive and these are intensive because we divided by mass. Now let's take a look at the intensive properties. Well, so let's take a look at the intensive properties in terms of, so we have pressure, temperature, V, U, S, Ke, PE, molar mass. Well, we can keep expanding, okay, E, etc. Well, if you look at these properties, you'll notice that there are some properties that probably depends on an observer. Okay, let me put velocity of the system and elevation of the system. So velocity and height or elevation are very special properties that people can disagree upon. In other words, it depends on the frame of reference. So that is not considered an intrinsic property of the system. And all properties that depends on velocity, so I'm circling them. Suppose the velocity and height we disagree upon, that means we can disagree upon Ke and Pe. And even E, because what is E? E is Ke plus Pe plus U. So these properties are called extrinsic. And the rest of the property are called intrinsic. I know this discussion is becoming esoteric, but once I finish this discussion, it will all make sense. So these properties that I'm listing here, Ke, Pe, E, etc., are extrinsic properties of the system. That is, they depend on who is observing them. So, well, out of these intrinsic properties, we can show that there are two kinds of properties. Well, intrinsic properties can be classified into two groups. One is called material properties. For instance, molar mass is a material property because as soon as you pick up the material, you know what your substance is. It's a copper block or aluminum block, and molar mass is fixed. It's intrinsic, but it doesn't depend on the state. On the other hand, P, T, V, U, S, etc., these properties and properties derived from them are properties that describe the equilibrium, and these are called thermodynamic properties. So a set of these properties tells you exactly what kind of equilibrium the system is at. If any of these property changes, that means the equilibrium has shifted to a new equilibrium. So this classification, if we turn it around, let me go to an animation and show you the classification summary. So we go to states and extended state. No, sorry. Let's go to system state. So let me just pause the animation here. Okay, that's all right. It doesn't pause. Doesn't have a pause button. So as you can see, this is a closed system going from state 1 to state 2. So in between what happens, we really do not care. But in the beginning, we are at a certain state. At the end, we are at another state. And let's just talk about those two states for the time being. So what we got here is that the properties of the systems are shown in layers. The core of the properties, as you can see, is the material property. What is the material property? They are properties that is determined as soon as you choose the material. Molar mass is already familiar with, we are familiar with. These properties we'll come across later on. Next to that is the thermodynamic properties that we just talked about, P, T, V, U, H, S. These are the properties that are responsible for defining the equilibrium. In other words, if these properties are observed not to be changing, that means the system has the same equilibrium. If you have a cup of coffee at a certain pressure temperature, and you'll find that all these other properties will have fixed values, if you isolate the system, it will never change. So if you put a warm coffee inside a container which is isolated from the rest of the universe, then we have the equilibrium defined by a bunch of properties, P, T, V, U, H, S. They will never change. Of course, the molar mass also will never change. So all intrinsic properties will remain same forever. But you can move this isolated cup of coffee at a different velocity. That will not change the equilibrium. That will change the kinetic energy of the coffee mug, but doesn't affect the underlying equilibrium. So these are called extrinsic properties. So velocity and height, as I said, they depend on the reference values. A person inside the system and outside the system may disagree on their values, and therefore all these other properties, Ke, Pe, etc., they are extrinsic because they depend on these arbitrary values. And finally, for this system, system state, we have total or extensive properties. Extensive properties are the total properties: total mass, total energy, total volume, total entropy, etc. And they depends on what? The mass of the system. So going back, we understand that if we know thermodynamic properties and velocity and height, or velocity and elevation, then we can immediately figure out all the extrinsic properties. Also, once you know, therefore we can evaluate all intensive properties, which means we also have evaluated the specific properties. If you know the mass of the system, then you can immediately find the total properties, total extensive properties. Now let me just introduce another type of system, another type of states. So we just talked about describing a closed system. Let's talk about describing a flow and how different that is. We'll soon see that it's not that different to describe a flow once we know how to describe a system. The flow we describe by looking at a particular cross-section. A flow is moving at a particular velocity. Probably there's a cross-sectional area of A. We all are familiar with the formula m dot equals rho AV, right? That comes from fluid mechanics. It's very simple to derive. Essentially, the unit is kg per second. What this equation comes from is that, essentially, think about it, in 1 second, if v is the velocity, suppose this is in 1 second it goes this far. So suppose this is the distance the fluid crosses in 1 second, and this is simply what? Density times area times that distance. So this is the mass of the fluid that will cross this cross section in 1 second. So therefore m dot equals rho AV. There is a more elaborate proof for that in the textbook you can go over, but I guess this suffices. Of course, density has to be in kg per meter cube, area must be meter square, and velocity must be meter per second. So if you look at the fluid that crosses a cross section, suppose we scoop out a little fluid, remember the assumption of local thermodynamic equilibrium. That fluid at a given time is at a particular thermodynamic equilibrium. So you can ascribe properties such as pressure, temperature, these are the pressure, temperature, V, U, S, etc. at a given location. So if we have location number 1, we'll call it a flow state 1. You have location number 2, we can call flow state 2. So we can talk in terms of velocity at 2 equals velocity at 1. That means this will be our way of representing the flow state 1 and 2. So similarly, m dot 1 versus m dot 2. Of course, in this case, probably m dot 1 and m dot 2 are equal, but we'll not assume that all the time. Will mean mass flow rate at state 1 and 2. One of the interesting things about flow state as opposed to a system state, so we are talking about flow state here, so let me write that down, is that notice in a system state what happens. We know, for instance, energy is given by m times E. Whereas in a flow state, energy is carried by a system. In other words, how much energy is carried every second? It will be E dot m dot times E. See if that makes sense. Here the unit comes from kg, kilojoule per kg, kilojoule. That's the total energy, stored energy of a system. In a flow, there's no concept of total energy of the system. There's a system flowing through the given location. So we want to find out what is the energy flowing every second. Every second, this much mass is carried by the flow. So therefore, kg per second, kilojoule per kg becomes kilojoule per second, kilowatt. So E dot means the rate of transport of energy. So we will come across this kind of rate of transport, and we can generalize this formula through what is known as a transport equation. It will be of this form, that E dot equals m dot times E, S dot equal m dot times small s. This is how much entropy is carried by the mass. Yes, entropy also can be carried just like energy. Or we can write even what is Ke dot. It will be m dot times Ke. Now that probably you haven't seen that kind of an equation before. Pe dot equal m dot times Pe. So what do these equations mean? They mean that they are also extensive properties of a flow, just like E and Ke and Pe were total properties of a flow. They were also extensive of a system. I'm sorry. So as you can see, E dot is Ke dot plus Pe dot plus U dot. Unit is kilowatt. And how do you find them? If you know the corresponding specific properties, it becomes very simple. So m dot times E, this is what it means. M dot times Ke, m dot times Pe, m dot times U. Well, we still don't know how to find U of a flow, for instance, or a substance. We'll figure that out when we do chapter 3. But we sure know how to find small ke and small pe. These are specific kinetic energy and specific potential energy. Therefore, we can figure out how much energy is carried by a flow. So that's a new concept. We are all familiar with kinetic energy, but we have not come across kinetic energy carried by a flow. It sounds weird, but if you think for a second, if I have a wind turbine generating power, electricity, well, a flow comes and essentially is tapping that kinetic energy that the flow brings. We know, just to give you an idea, so all other energy carried by the flow is not important in case of a wind turbine. How much energy does the kinetic energy does the flow carry? M dot equals rho AV. We know this formula, and you must memorize this formula. You will come across m dot equals rho AV in fluid mechanics and other thermal science classes. And what is specific kinetic energy? V squared by 2000. Recall, specific means per unit mass. I divided by mass already. So these two terms, when you multiply, notice what it becomes. It becomes rho AV cubed by 2000. So that's why the energy that is coming towards the wind turbine goes with velocity cube, not velocity square, as somebody might intuitively say. Why velocity cube? Because the kinetic energy depends on velocity square, we all know. And how much mass is coming, that depends on velocity. That's why it becomes velocity cube. So let me just summarize the classification of a flow state with the same animation. If you click on flow state, again, that's an extensive state. In other words, all kind of properties are included here. But notice that state 1 and 2 in this flow, the two flow states in the inlet and exit of this valve, it doesn't matter what device it is, At the core is the material properties. Again, we have talked about material properties. If the fluid is H2O, then molar mass will never change. Then we have these thermodynamic properties, pressure, temperature, VU, S. We have encountered not all of them, but most of them. And these describe what? The equilibrium, the thermodynamic equilibrium at a given location. And they are no different from thermodynamic properties of if I have the fluid inside a tank, a system state. And of course, we have the extrinsic properties that depends on the whim of the observer, and these values are not intrinsic. So they are, you notice that we also have color-coded properties. The material properties are always in red in our symbolic notations. Thermodynamic properties in blue, extrinsic properties in green layer. And finally, instead of total properties, now we have what is known as transport properties. Remember, for a system state, we had mass, entropy, volume, etc. Now we have m dot, s dot, v dot, etc. So that is the big difference that what we got here. So this particular animation kind of classifies properties pretty well. We have already talked about system state, and this is flow state. And to understand thermodynamic properties, you will notice that they're independent of whether you're talking about a system state or flow state. If you go to thermodynamic state, you will find these are basically material and thermodynamic properties that describe the equilibrium for both flow state or system state. Before we finish, let me just talk about a couple more properties, and we'll be done with all the theory we ever need to understand a system or a flow. So we talked about the energy carried by a flow. I want to expand on that a little bit. So suppose this is state 1 or this is state 2. These are different flow states. Now, what is the energy carried by a flow? The first impulse will be, well, every second, how much energy is carried by the mass? Suppose this much amount of mass is crossing this boundary every second. So we know exactly how much mass is crossing every second. That's m dot at 1. And how much energy is carrying? Per unit mass, it carries small e, is the stored energy per unit mass. So this must be the energy that it crosses. This is the energy carried by the mass or transported by the mass. But is that all the energy that crosses the boundary? Recall from our discussion of external work and flow work that when the mass is pushed into the system, it generally doesn't flow in its own will. For a mass to move in, there must be work done. And let's consider this is our system. Let me just draw the system boundary so that this discussion is clear. So our system is this bunch of pipe. A big pipe is our system. So at state 1, things are entering. At state 2, things are coming out. Let's just consider state 1. The flow will not go in. Suppose inside the pipe there's a very high pressure. Then to get the flow in, somebody must be pushing it in. So the pressure at this point has to be P1, whatever that is, for the flow to be pushed in. So this mass, as it is pushed in, how much work is done? So that work that is done every second is called the flow work. So really the energy that is crossing the boundary is this plus the flow work at location 1, which I can write, again, go back to the discussion of flow work, which we did on module 0. The flow work was shown to be force times velocity, pressure at 1, area at 1 times velocity. So this is the total energy that is called the flow energy. So if we can keep expanding this term to simplify it, we can call it m dot 1 E1 plus P1, I want to bring a rho density, so we can say this is rho 1 A1 V1 P1 by rho 1. So I multiply and divide by rho 1. But I notice that this guy is nothing but m dot 1. And we also know P1 over density is nothing but the thermodynamic property specific volume. So notice how it's simplifying. And this is a very important concept. We will use that anytime there is a flow involved. So the energy carried by a flow, or the flow transport of flow energy, is given by mass flow rate times another specific property. Because look, E is a specific property, P is a specific property, V is a specific property. Defining this as J, we can write it is m dot 1 times J1, where what is J? This is a combination of two properties, E plus PV, whatever that means. So E, we understand, is energy per unit mass, stored energy per unit mass of a system or a flow. Pressure, we understand. Specific volume, we understand. So the unit here must be kilojoule per kg, just like E. So summarizing, if we know E, P, and V, we know J, which means whenever we want to find out the energy that is transport of flow energy, what does it mean? So the symbol will be capital J dot, which is E dot plus W dot flow, which turns out to be m dot times J, where J equals E plus PV. We already know what E is, KE plus PE plus EU, right? It so happens that EU plus PV appears everywhere together, and that's given another new name, KE plus PE plus H, where H is called specific enthalpy. Well, it's just a name. You can take different properties, combine them, and call it a new property. It so happens that U plus PV appears everywhere. So how will we understand enthalpy? Again, it will become an important property. Well, to understand enthalpy, if you go back what J is, and to understand J is to understand J dot. What is capital J dot? It is the energy, that is the net energy carried by a flow. What is capital E dot? The stored energy carried by the flow. Stored energy means if the if mass is hot and it moves, it carries more energy. If it's hotter, it carries more energy. Whereas it also, as it crosses a cross section, it also depends on what the pressure there, because a lot of flow work is involved there for the flow to move in. That's why there is two different terms combined to get flow energy. The rate of transport of flow energy is given by J dot, where J is flow energy per unit mass in the unit of kilojoule per kg. So J tells you if a flow is going to a place from wherever it's entering or getting out, it is carrying how much energy per unit mass. And H, therefore, is a very similar thing, except H plus K plus P is the J. So if Ke and P are negligible, J and H are the same. So the enthalpy can be looked upon as the flow energy per unit mass when kinetic and potential energy are not large. So we'll stop here and expand these ideas through a couple of problems.